Before we dive into the differences between vertical and horizontal scaling, let's first define what scaling is. Scaling is the process of adding more resources to our application to handle the increased load. This can be measured in terms of requests per second, concurrent users, etc. Scaling horizontally and vertically are similar in that they both involve adding more computing resources to our system. They just do it in different ways. Vertically scaling, or scaling up, means more resources, CPU, memory, etc. to a single server. This is usually done by upgrading the server's hardware, meaning adding more RAM, CPU, etc. Vertical scaling is straightforward, but it's usually limited to the hardware and can be quite expensive. Horizontal scaling, or scaling out, means adding more servers, nodes, machines to our system. Consequently, this means that we need to distribute the load across multiple servers, which is typically done using a load balancer. When deciding between vertical and horizontal scaling, we need to consider the pros and cons of each approach. For example, in a database world, horizontal scaling is usually based on the partitioning of data. While with vertical scaling, scaling is done through multi-core, for example, by spreading the load between the CPU and RAM resources of the machine. With horizontal scaling, we're not limited by the hardware, but we need to deal with other additional complexity, such as load balancing, data consistency, etc. In this lesson, we'll demonstrate how horizontal scaling works in practice by increasing the number of instances of our service using Docker Compose. Note that in real-world systems, you would use a container orchestration tool such as Kubernetes to scale your services, depending on different metrics such as CPU usage, memory usage, traffic, etc. We won't be able to dive into Kubernetes since it's a bit outside of the scope and complexity of what we're trying to learn in this course. So, let's get started by opening up our Docker Compose YAML file and adding a new deploy property to the Workflows service. Let's save our changes, recreate our containers, and start everything up with Docker Compose up. As we can already see in the logs, there are multiple instances of the Workflows service running now. See the 1, 2, 3 suffixes on everything. Next up, let's navigate to the Workflows service file and declare a new private variable, logger, as follows. With this variable in place, let's update the create method to log that we're creating a new workflow. Let's save our changes, head over to the terminal, and create 3 buildings using curl. Now, let's switch to the other terminal window and check those logs. As we can see, instead of distributing the load between multiple instances, NATS delivered the message to all instances, which is known as broadcasting. But that's actually not what we want. Let's fix that real quick. In NATS, when subscribers register themselves to retrieve messages from a publisher, the 1-to-n fan-out pattern of messaging ensures that any message sent by a publisher reaches all subscribers that have registered. NATS provides an additional feature named Queue, which allows subscribers to register themselves as part of a queue. Subscribers that are part of a queue form a queue group. So, how can we configure our subscribers to be a part of a queue group then? Well, we can do this by passing the queue option to the server configuration. So, let's open up the main TS file in the Workflows service application and update the connect microservice method to pass the queue option to the server configuration. Let's save our changes, head over to the terminal, and create 3 buildings once again using curl. Switch to the other terminal window, and once again, let's check those logs. And look at that. As we can see, the load is now distributed between multiple instances of the Workflows service. Great. As we mentioned at the beginning of this lesson, in real-world systems, you would use a container orchestration tool such as Kubernetes to scale your services, depending on different metrics such as CPU usage, memory usage, traffic, etc. In our case here, since we're just doing things for demonstration purposes, we simply hard-coded the number of instances in our Docker Compose file.